Okay, welcome everyone to our Thursday afternoon seminar, which is actually the last seminar of the season. So it's a great pleasure to have with us Tevong from CERN, who will tell us about self-organized localization. So please, you have the floor.
Hey, thank you very much for having me. It's a pleasure to virtually visit Madrid again. And please feel free to stop me at any point to ask questions. I don't see the hand being raised, so just stop me and ask if you want to have more details on any of the things I'm going to talk about. The paper is based on this work with Jan Giudice, Matthew McCullough here at CERN. And the outline of my talk is basically as follows. I will start with some motivation about why we're interested in looking at critical phenomena and quantum phase transitions. And the big picture that we start out with is concretely realized in terms of solving the dynamics of the Fokker-Planck volume equation. So I'll explain a bit what I mean by the dynamics of the Fokker-Planck equation and how the different regimes of these dynamics are of interest for dynamics during inflation in the early universe. And adding quantum phase transitions to this story is what leads to self-organized localizations, in particular, the extra conditions from these phase transitions of satisfying continuity and flux conservation. Then I'll apply these new solutions to self-organized localizations that might help to explain some well-known problems of, for example, metastability, the Higgs mass, and the cosmological constant, before concluding with a brief discussion of the measure problem in eternal inflation. So let's start with the motivation. And essentially, the main picture that I want to emphasize is the idea of the critical point being a very special place in a wide range of different situations that we might find the system to be in. And in many systems, if we have a classical phase transition, to be at the critical point, we know that we have to set this up in a very fine-tuned way by dialing, say, the temperature of a system to lie just at a certain critical point. So this is a highly non-generic situation in terms of many systems that we know about. And to find ourselves at the critical point of a system implies essentially some kind of dialing that is being done somehow. And this aspect is puzzling in the same way that a fish living in a pond that is just about to freeze but hasn't quite frozen yet would find itself puzzled to ask why it's not in the purely liquid phase and why it's not purely in the frozen phase, or why it hasn't frozen and died yet, but it finds itself just at the boundary. So similarly, in our universe, we find three maybe puzzles that require some kind of explanation in a similar way. The first is the well-known Higgs potential metastability, which comes about from the experimental measurement of the top mass and the Higgs mass, which in the standard model leads to the very non-generic situation of finding ourselves in this sliver of metastability, when in principle we could have been anywhere in the huge region of stability, and even in the instability region, which would have for sure signaled some kind of new physics that would have to restore the Higgs potential. But instead, we curiously find ourselves, just like the fish, on the critical boundary of two phases coexisting. The second hint is the naturalness problem of the Higgs mass, where in principle the Higgs mass could have been anywhere from minus m squared to plus m squared, where m is the cutoff of the theory that could be anywhere from the TeV scale to the Planck scale, and yet we find the Higgs mass to be relatively light with respect to these possible scales. So this is like living in a vacuum that is just at the boundary between electroweak symmetry being broken and unbroken, where it isn't very strongly broken, nor is it strongly unbroken. We seem to be just at the critical point between order and disorder of these phase transitions. And finally, the perhaps most well-known and biggest problem of naturalness is the cosmological constant. And in this case, the typical scale could be from minus m Planck to the fourth to m Planck to the fourth. And we find ourselves again at the boundary between implosion and explosion, where we live in this small window that could be anthropically selected in some way, but could also, which slide are you seeing it? Okay, so you're now on the right slide. So the anthropic window would limit the range of the cosmological constant, as famously argued by Weinberg, but still there could be some room within that explanation for why the CC is really what it is. Okay, so the three hints for near-criticality are explained in conventional ways. For metastability, this could be simply that new physics restores the stability of the Higgs potential, which is always a possibility. In our case, we want to assume that whatever heavy new physics there is does not restore the stability, and we want to take this hint seriously as a possible coexistence of phases that our universe really is in. The second hint of the Higgs mass is typically solved by requiring new symmetries at the TeV scale, which is either supersymmetry or composite Higgs typically. But the lack of new physics at the TeV scale is not necessarily a problem, in that it might just be a bit more fine-tuned than we expected, and we could still discover this new sector around the corner. But as it gets heavier and heavier, we might also want to take more and more seriously the possibility that it is not there at all and consider alternative principles that might be at play. And this is in particular supported already by the cosmological constant, where we are lacking any kind of symmetry-based explanations that can satisfactorily explain the very small cosmological constant problem. And the anthropic explanation only goes so far, in that even within the anthropic window, there is a wide range of possible values for the CC. And if you allow other parameters to vary simultaneously, then that window could widen even further. So a dynamical explanation could still be important. Yep.
Can I ask a quick question here? This comment you made about metastability, etc., and then possibly new physics. Of course, the fact that in the standard model we're in a metastable situation, most likely, is, I think, often relief. For example, in SUSY, I think it's not a metastable one. So this problem at that moment doesn't exist anymore, or it only applies. Exactly. Yeah.
Yeah.
So new physics could also solve several things at the same time. Then, yeah.
Yeah, exactly. This is why I say in this 3 points here that the usual answers to these problems for metastability, it's almost trivial that new physics can easily restore the stability.
Yeah. Yeah.
And for the Higgs mass, yes, supersymmetry is obviously the dominant solution for these things.
Of course, cosmological constant not.
Right.
As far as I know.
So exactly. So the CC is already like an elephant in the room that suggests maybe we should be looking at other principles. The lack of new physics at a TeV scale, I would say, is not necessarily that serious yet, in that I'd be perfectly happy with supersymmetry still solving TeV scale naturalness. The metastability thing could be trivially explained with new physics. Again, you just add any kind of scalar or gauge bosons and so on, and their contributions to the running would restore the stability. But it still seems like the fact that in the standard model itself, there's this coincidence, let's say, it didn't have to be in that sliver of metastability, might be that there really is this metastability in our universe. So it's, I wouldn't say it's a big puzzle, it's just perhaps something that we could take as a hint. And indeed, we'll see that in the mechanism that we're proposing, the self-organized localization, one of the core predictions is the fact that we should be living in a metastable universe. So it's an interesting curiosity that our standard model vacuum appears to point towards this. So that's the motivation. Now, the new principle at play that I want to present here is self-organized criticality, which is a phenomena that we already know exists in nature. And we already know that many systems in nature are self-tuned to live near criticality. This was first pointed out by Bach, Tang, and Wiesenfeld in this paper from 1989, where they consider there the prototypical example of the sand pile, where the grains of sand dropping on the slope of the sand pile, given enough time, would find itself at the critical slope. So an ant living locally on this sand pile might question why the slope just happens to be the right gradient, such that the sizes of the avalanches follow a scale invariant pink noise distribution. When had the slope been slightly shallower, then the sand piles would never trigger an avalanche. Had it been steeper, then it would always trigger large avalanches. And yet it's located just at the right critical slope. So the ant might think this is just a coincidence, that the slope just happens to be this value. But it turns out that any sand pile given a long enough time would find itself in equilibrium to self-organize itself to be at this critical gradient. And since then, there have been many other systems that have been pointed out to self-organize to live close to criticality. So unlike in classical phase transitions, where one has to tune to really live there, it turns out that the equilibrium distribution of many systems self-organizes to live at the critical point. So I show here an example in the brain, which in the last decade has gained acceptance as a theory for why the brain is self-organized to live at a critical point, where the avalanches of neurons triggering other signals in other neurons is not too ordered and not too disordered, but just at the boundary of these two regimes. And this has been applied to explain evolution and explain financial systems and many other types of equilibrium dynamics. Now, to explain fundamental parameters in terms of self-organization, obviously requires some more concrete mechanism. And I think the general idea has been proposed many times in the past, including Jan about a decade ago. But only recently has some more concrete principles emerged. In particular, Justin Corey and these series of papers has proposed self-organized criticality in an eternal inflation landscape, which is a very different approach to ours, in that his approach uses the vacuum transitions in the whole string landscape as the system which self-organizes itself through these transitions. In our case, we want to focus on one vacuum and look in particular at a patch of one particular vacuum. And what we show is that quantum phase transitions during inflation can localize the scalar fields fluctuating along that patch of that vacuum at the critical point of the phase transition. So this is the self-organized localization that is tied to phase transitions that I will talk about. To explain what I mean by a quantum phase transition, I mentioned that classical phase transitions have to be tuned to be at a very particular temperature to live at the critical point of a phase transition. So this is like varying the background temperature in cosmology or varying the background magnetic field in a condensed matter system. A quantum phase transition, by contrast, achieves a phase transition not through temperature fluctuations, but through some varying background field. So in the Ising model, this could be through varying a magnetic field, or in cosmology, this would be a scalar field that varies. For example, in this case, phi is coupled to some other scalar psi, and this scalar psi has a Z2 symmetric potential, which as phi goes from 0 to some non-zero value, tilts this potential and triggers a phase transition. So this is what I mean by a quantum phase transition. It's not necessarily quantum in maybe the sense that you're imagining in terms of tunneling, which it could be due to tunneling, but it could equally well just be a second order phase transition. Okay, so that's the big picture. Now, the actual mathematical framework in which we want to solve for the dynamics of these distributions is the Fokker-Planck equation. So this is the dynamics of the scalar field phi, which satisfies a Langevin equation in which its equation of motion undergoes some classical drift due to the potential, together with some stochastic fluctuations, where this stochastic term is randomly drawn from a Gaussian with Hubble width to parameterize the Hubble quantum fluctuations. So this framework by Starobinsky and developed by others since is to take the volume average Langevin trajectories, where if one averages these Langevin trajectories over many, many trajectories, then one gets the Fokker-Planck equation. If one includes also the volume expansion that comes from inflation, where higher energy densities will inflate exponentially more than lower energy densities, then one adds to the Fokker-Planck equation this volume term. So in the Fokker-Planck equation, without the volume term, P would be a conserved probability distribution. But with the volume term, P becomes a volume distribution that isn't conserved, since the volume is continuously expanding during inflation. But the predictions for which value of phi will become more likely than others is the volume that dominates the universe over the volumes with other values of phi. So the game is to solve essentially the volume distribution P by solving this equation. And the quantum diffusion term is the first term in this FPV equation. The second term is the classical drift term, and this third term is the volume term. And it is the competing effects of all these terms that determine the different regimes of whether or not the distribution can go up the slope or down the slope, and where it ends up localized. As I mentioned in the introduction, I'll come back at the end to the measure problem, which is related to the ambiguity in choosing the time parameterization during eternal inflation, where one can choose different hypersurfaces of constant time, depending on how one parameterizes time, which in this case can be chosen by a parameter xi, and redefining time in this way, we have a one parameter xi that is 0 when we have proper time, 1 when we have proper time, and 0 when we have what's known as scale factor time. So this can affect the predictions of the distribution, and this is why it is called a measure problem, because one has to choose how one essentially measures the different volume distributions. Now, the important thing to remember is that phi in our case is not the inflaton. So the inflaton is some constant background that we assume dominates the energy density of the universe during inflation. And this phi field is a subdominant energy density. We call this an aperon field. And this aperon field is essentially what's fluctuating in this background and is scanning some fundamental parameter as it does so. So we restrict ourselves in particular to an effective field theory field range, where we normalize phi, the dimensionful phi, by the typical field range F. So the dimensionless phi will be some order 1 number. In this parameterization, we can also factor out the dominant energy density contribution to the potential with the inflationary Hubble H0. And we also then write the contribution from the aperon potential in a way where omega phi is a dimensionless potential, and we take out a dimension full factor f to the 4 overall outside here, with g epsilon being some small parameter. So omega phi is some order 1, also a number. And in particular, because we're interested in an EFT field range, we can always expand locally around around whatever the potential is in terms of the linear potential, quadratic potential, and so on, where it's sufficient to keep the linear contribution for our purposes. We also have results for a quadratic potential in the appendix, but in general, the dynamics don't depend on the details of the form of the potential within an EFT field range. So expanding around the constant inflationary Hubble with the subdominant energy density contribution, where we parameterize the aperon potential in this order 1 omega phi, which you can basically just take to be a linear potential. So when you see omega phi, just imagine this is just a linear potential phi. This is the Fokker-Planck volume equation that we want to solve parameterized in terms of alpha and beta. So alpha is a dimensionless quantum diffusion parameter, which parameterizes the sizes of the quantum effects. The volume term beta is parameterized by the ratio of f to m Planck. So the typical field range f, we see it has to be greater than m Planck for this beta to be greater than 1, which is the regime we'll be interested in for the volume effects to be important. So we are in the super Planckian field regime necessarily. And in this parameterization, the classical drift term is just an order 1 number. Since phi is order 1, the derivatives of phi will be order 1, omega prime is order 1. And this allows us to see immediately the relative sizes of the terms, where we typically want to be in the regime where alpha is less than 1, since we don't want the quantum terms to dominate. We want beta to be greater than 1, so the volume term is important. And this parameterization is useful to then also see that the typical relaxation time, which is a typical time scale in this equation, is the relaxation time because this is the time that it takes for a slow rolling field along this potential V to explore a typical field range F. And rewriting this relaxation time in terms of alpha beta times this quantity SDS is interesting because SDS is the entropy bound, the ratio of m Planck to h to Hubble squared. And the entropy bound is the maximum number of E-folds that allows for eternal inflation to be non-eternal. So the fact that the relaxation time is alpha beta times the entropy bound, and we're interested in the regime alpha beta being greater than 1 for the volume effect to dominate, to be in the quantum regime where we go up the potential, implies that we have to violate the entropy bound and we are necessarily in the eternal inflation regime. This is for the quantum regime. There is a classical regime where we have solutions where alpha beta is less than 1. As we'll see, that's also interesting for application to the cosmological constant solution, in which case we are not necessarily in the eternal inflation regime, but practically we typically will always have to be in this eternal inflation regime. So what we are interested in is the asymptotically stationary equilibrium distribution. So the stationary distribution obtained by separation of variables and solving for little p for the different eigenmodes with eigenvalues lambda, we see that lambda dictates essentially the inflation rate of the different solutions. So a general solution will be a sum over all the contributions of all the stationary solutions, depending on your particular setup and boundary conditions. But asymptotically, the one that remains at late times will be the one with the largest eigenvalue, since that's the one that will inflate the most and will be projected out from a general superposition of these solutions. So the nice thing about this framework is that it is insensitive to initial conditions, and we can obtain a late time equilibrium distribution with very general considerations. The little p solution here is solved explicitly, but we can get qualitative features of this solution. In particular, we are interested in where the most likely value of phi will be, which is the location of the peak of the volume distribution. And this is determined by the eigenvalue. So one way to see where the peak location will end up without even having to explicitly solve it is the consideration of positivity for the asymptotically stationary solution. The fact that the volume distribution at equilibrium is a positive quantity means we can immediately discard all the solutions that go negative before reaching the boundaries. So if we require a vanishing solution at the boundary, then the discriminant is a quantity that determines whether or not the solution will go negative or not. The discriminant is basically just saying, if we take this equation locally and we look at this as a quadratic equation locally, then the discriminant of this quadratic equation going negative leads to an imaginary solution that oscillates negative. So if it vanishes at the boundary, then the discriminant must be just about to go 0 at the edge of the field range, which in these dimensionless units is at 1. And this then tells us what the maximum eigenvalue is that can remain positive everywhere in the EFT field range. Once we have this maximum eigenvalue, we take the Fokker-Planck volume equation at the peak location, which by definition is where the gradient of the distribution is 0, and rearrange this in terms of the eigenvalue, telling us where the location of the peak will be, parameterized by beta, where beta is greater than 1, and this is an order 1 term, and this is also a small term. So basically, you can forget about the last 2 terms, and this is telling you that the eigenvalue determines where the peak location is. So given that we have the maximum eigenvalue, we just plug that in, and this tells us the peak location wants to be at the edge of the boundary, as high up the linear potential as possible, minus some order 1 number divided by alpha beta. So in the regime where alpha beta is greater than 1, the peak location will be as high up the potential as allowed by the boundary conditions. If alpha beta is less than 1, then it wants to be as far down as possible. So this is summarized here in terms of the linear potential on the left here, which is centered at 0. But this is just the general EFT patch of the potential from -1 to 1. And the classical regime is when alpha beta is less than 1, we see the solution here explicitly solved, is plotted here and is as far down the potential as it can be. The QV regime where alpha beta is greater than 1 is plotted here and is close to the end. But this estimate that I showed on the previous page breaks down when the location of the peak is closer than the typical width to the edge. So this is when the peak is a distance 1 over alpha beta from the top. And the values of alpha beta are such that it is too close to the top. So the width is 1 over square root beta. And the condition that this peak distance is closer than the width is when alpha squared beta is greater than 1. So then there is another solution, which is the Q squared B regime, in the regime where alpha squared times beta is greater than 1, where the peak is as close to the top as possible. It's about to oscillate to go to 0, with a distance comparable to the width, which is alpha over beta to the power of a third. So these are the 3 typical regimes that we are interested in. And to plot this on alpha versus beta, as I mentioned before, if beta is smaller than 1, then the volume effect is not important, and we just have the usual Fokker-Planck dynamics without significant volume expansion effects. If alpha is too small, this is Hubble becoming too small. At some point, there is no slow roll in this Fokker-Planck dynamics. For beta greater than 1, the non-perturbative region, if Hubble is too small, is when the inflationary energy density is no longer set by the inflaton, which it has to be if we want the universe to reheat while maintaining the stationary distribution of the apparent field separately. So something else has to be the inflaton. We can't have phi be the inflaton. And if we have too large of a Hubble value, so alpha is greater than 1, then the quantum regime is just featureless and boring because quantum effects dominates over everything else and everything just diffuses out. So we're interested in these 3 regimes here. Okay, finally, the quantum phase transition part of the story is what is specific to self-organized localization. And this involves solving the Fokker-Planck equations, as I mentioned in the previous slides, with the additional conditions that come about due to the phase transitions when phi scans another field. So what we see here on the top left is the linear potential that I showed before, where we understand the dynamics now of when the solution goes down or up. But what happens at this point here is that as phi is scanning some other potential, let's say this psi example that I gave before, then when it reaches the critical point, which we placed at 0 by a shift of the coordinates, but there's no loss of generality in placing the critical point at 0, then this triggers a phase transition that, from the phi potential point of view, leads to a discontinuity in its potential when psi transitions in a first order phase transition from one point to another. So this discontinuity in the potential of phi leads to a discontinuity of p prime, and requiring continuity of the Fokker-Planck volume equation across the critical point means that if we integrate across the critical point, the Fokker-Planck volume equation, this gives us essentially a matching condition that the difference in the gradients of the volume distribution across the critical point must match up with the discontinuity in the gradient of the potential across the critical point. So this is no different to undergraduate quantum mechanics, where we solve for the Schrödinger equation in a square well potential, and the potential has a discontinuity across the different boundaries, and one has to match across these discontinuities. And the solutions that we obtain are then plotted on the top right, where we see again the feature that the classical solution is as far down the potential on either end, and we have these kind of twin peaks around the critical point. So this is a toy model in a sense that we are treating essentially the phase transition as instantaneous, and this is effectively the picture that one would see if one zooms out enough. But if one zooms in, then the phase transition, the features of the microscopic phase transition can be important in terms of determining the solutions at the critical point. The other condition is that when one has a phase transition from one sector to another, then we require flux conservation across the transition point. So in this case, we have, let's say, a very flat potential in some hidden phase and some visible phase that has a linear potential. And beyond the critical point, at some point, the flux will tunnel or slow roll, depending on the dynamics, and transition from one phase to another. And the conservation of flux at the transition points leads again to a flux conservation condition that one has to take into account when solving the Fokker-Planck equation on the visible phase. So the solution here is plotted on the right. In this case, the regime that we're interested in here is the classical regime, because in the quantum regime, we know that the solution wants to go as far up as possible. So here we are in the classical regime, and where the peak is located is determined by the solution that satisfies the conservation of flux at the transition point and the choice of boundary conditions at the edge of the effective field theory range. So with the boundary condition that we have a non-zero flux at the edge of the field range and satisfying the flux conservation with this hidden phase, the solution is localized at the critical point, and we see here the peak of the volume distribution on the visible phase, which is rescaled by this factor to appear on the same size as the hidden phase. This is just to say that the probability to be on the hidden phase is much, much smaller than the probability to be on the visible phase. So I'll come back to the solution in the cosmological constant example. So now that I've described a bit how self-organized localization works in terms of Fokker-Planck dynamics with these conditions that have to be satisfied at quantum phase transitions, I'll now discuss how they can address the metastability coincidence that we observe. So in this case, phi is now scanning the Higgs quartic, and the Higgs quartic is taken to be negative when phi, is taken to be positive when phi is negative. So again, we shift coordinates of phi without loss of generality to place the critical point at 0. So in this IR phase, we have the Higgs potential with a positive quartic, and we call this the IR phase. And as phi is getting closer and closer to the critical point, the quartic starts becoming negative beyond the critical point. And as it becomes negative beyond the critical point, we are then in the UV phase, where we have the at some point we have the coexistence of the IR and the UV phase. This is why we have this line actually extending, because at some point beyond the critical point, we don't have an immediate transition, as in the toy example. We have a supercooled phase where the Higgs wants to transition but hasn't quite yet, until phi reaches some value phi star, at which point the potential has a sufficiently negative quartic that it definitely will transition beyond this phi star. So, and then beyond this phi plus point, then the IR phase doesn't even exist anymore. There is no longer a minimum in the IR. And we are left with purely this UV minimum. So we assume the Higgs potential is restored by some new physics at the EFT cutoff. So this gives a Fokker-Planck volume distribution that localizes phi near the transition point. And this localization at the transition point is precisely why we find the standard model value to be in this metastable region. And the prediction from this mechanism is shown by the solid black lines, which are the different values of Hubble during inflation. And for a value of about 10 to the 10 GeV, we see that depending on the cutoff, big M, we can be in this region here. So this is perhaps shown a bit more intuitively here, where the x-axis is the values of Hubble that is required to be within 1 and 2 sigma of the observed standard model value. And the y-axis is the cutoff of the theory M. If we take M to be too large, then at some point the energy density of the apeiron will dominate over that of the inflaton. Hence, we shaded this gray region out. And also, if the Hubble fluctuations are too large, then the Higgs can no longer be taken to be sitting in its minimum. And one then also has to include the Fokker-Planck dynamics for the Higgs, which for sufficiently large Hubble may mean that it will also climb its potential, and the whole setup becomes more complicated, and one has to solve a two-field Fokker-Planck volume equation. Hence, we grade out this region here. So this is the Higgs metastability example. The other example is that of naturalness of the Higgs mass. And in this case, phi, the apeiron, is coupled to the quadratic term of the Higgs. And this solution is separate from the other one. One could potentially scan both simultaneously and try to explain both in a more complicated setup. But in this case, we are just trying to explain the Higgs mass solution. And the way we do this is by scanning the quadratic Higgs term with phi, where in this case, we have 3 different phases. So in the electroweak phase, electroweak symmetry is unbroken, and we have this green potential here for the Higgs. So the Higgs is just sitting at its IR minimum. And as we know from the running of the Higgs quartic that leads to the standard model metastability, we have a UV vacuum that we again assume is restored at the EFT cutoff. And this is why in this case, we have the coexistence of the UV vacuum together with the IR unbroken vacuum. And as phi is scanning the Higgs to become more and more negative, in the IR phase, we have this blue potential. And in this case, electroweak symmetry is broken, and the Higgs is sitting in its value at 246 GeV or so. But if phi keeps going past the critical point where it becomes more and more negative, at some point the IR vacuum disappears and the whole thing collapses to just a single vacuum in the UV. And this is the yellow UV phase that is shown here. And again, the solution will be peaked close to the transition point, which is the mechanism that we're using is the transition, not from the unbroken to the broken transition, but the broken IR to the broken UV phase transition. The reason is that the unbroken to broken phase transition is second order and too small to be sufficient to really localize the solution at the critical point. It is possible to do it with a very low cutoff, about 1 loop above the weak scale, but in general, one needs some extra effect, large effect to be triggered, which could be, for example, QCD in the relaxon solution. QCD is triggered at that point, or in other solutions that people have considered, there is some other trigger that leads to a large effect. In our case, we want to use the broken IR to broken UV phase transition, which is a large effect due to dimensional transmutation. And this leads to a large separation of scales in a natural way between the instability scale lambda I and the cutoff of the theory. And the Sol mechanism would predict the volume distribution to be peaked close to the instability scale, which is why this phi plus, the location, is very close to the instability scale. And this is what sets the weak scale. So the prediction is that the weak scale is close to the instability scale, which is technically and naturally much smaller than the cutoff. Unfortunately, in the standard model, we know that this instability scale is 10 to the 10 or 10 to the 12 GeV. And to then explain the weak scale being what it is, we require new physics at the TeV scale to lower this instability of the Higgs potential down to about dV. This can be done naturally through the addition of vector-like fermions. So if the hints for new physics at the TeV scale are true in B anomalies or G-2 or some as yet undiscovered new phenomena at the TeV scale, if it happens to be due just to vector-like fermions, and these vector-like fermions couple to the Higgs, then their contribution to the Higgs quartic will be negative and will lead to an instability that could be very low. This would have some motivation as well from this Sol framework, in the sense that if the Higgs is the only scalar that is tuned by this mechanism to be light, then we expect any other scalars to be heavy, and any gauge bosons that get their masses from scalars will also have to be heavy. So there is some reasoning for why we would expect then to only have vector-like fermions at the TeV scale. There is still a little hierarchy in that an instability at the TeV scale would still predict the Higgs Rev to be at the TeV scale. And some early transitioning could then lead to this little hierarchy, which could be arranged by having Hubble be a specific value that allows for an early tunneling. And this little hierarchy problem is very similar to the little hierarchy in composite Higgs, where the Higgs wants to be at the compositeness scale F, but some dynamics has to be arranged to have a little hierarchy of the ratio V over F. Similarly, we need a little hierarchy V over lambda I. And finally, the cosmological constant solution is perhaps the more counterintuitive of all these different types of solutions, because in this case, as I mentioned before, the way the solution picks out a small value of the cosmological constant in our vacuum is perhaps less physically intuitive, because here we don't want the solution on the visible phase to climb up to potential as far as it wants to go. So unlike the other two solutions, we are not in the quantum regime, we are in the classical regime. Now, to solve the Fokker-Planck equation, one requires boundary conditions. And in the classical regime, there are two types of solutions. There are always two solutions to a second order differential equation, and which solution is picked out is determined by the boundary conditions. The solution that we pick out from the non-zero flux at the boundary condition is the one that is peaked somewhere along this distribution due to an interplay between the volume term and the classical drift term. The other solution is known as the Gibbs solution, is the one where the quantum diffusion term and the classical term dominates. And this is the classical solution that simply goes down as far down the potential as it wants to be. So the non-zero flux at the boundary condition is essential to pick out the other solution that is peaked somewhere along along this potential. But from the point of view of someone living on the visible phase, there is no reason for the distribution to be peaked anywhere over any other location along this potential. So why does it end up peaked precisely at this point is due to the flux conservation condition at the transition point with the hidden phase. So the hidden phase, one can solve for the solution there, which determines the eigenvalue, the maximum eigenvalue that determines the asymptotically stationary solution. And this maximum eigenvalue determined by the hidden phase, as I mentioned before, determines where the peak of the visible phase solution will be. And what we see here is that the peak phi bar on the visible phase will be where the energy density on the visible phase wants to match the energy density on the hidden phase, where this term is very small. Hence, the solution wants to be localized at the point of vacuum energy degeneracy. And this VI is the constant contribution from the inflationary background, which uplifts the solution to have energy density VI. And after inflation ends, this constant is removed for both, which still means that in our present universe, we are localized at this point of vacuum degeneracy. So this explains the small cc in our visible phase, because the hidden phase, vacuum, has a 0 cc, which is enforced by an unbroken supersymmetry in this hidden phase and R symmetry, which allows the cosmological constant to vanish in this hidden phase. So in our visible phase, supersymmetry is broken, but essentially cosmology and eternal inflation will localize us at the point of vacuum degeneracy with this hidden phase. This is essentially a kind of equilibrium dynamics that is reached through a very long time during eternal inflation. So to conclude, the point I want to emphasize in the take-home message, if all the details went over your head, then the main physical message is that scalar fields undergoing quantum fluctuations during inflation can be localized at the critical points of the quantum phase transitions. So this self-tuning mechanism essentially predicts why we happen to be at the boundary of two different phases. So this is one key feature, let's say, of self-organized localization being an effect in our universe, is that through measurements of parameters like the top mass and the Higgs mass in the standard model, or the potential discovery of only vector-like fermions at the TeV scale and nothing else, if we can infer that we are definitely in a regime of metastability, this would be highly suggestive of some kind of self-organization being at play. For the cosmological constant solution, it's a bit more difficult to determine the existence of this hidden phase. But if we were to measure some non-zero W parameter that suggests evolving dark energy, because in our model, phi would still be slow evolving now on a very flat potential, it wouldn't have slow evolved sufficiently to modify any of the predictions, but this could be detectable in the form of dark energy. So finally, the measure problem is one big problem of predictions in eternal inflation in general. This is quite notorious in the sense that the Fokker-Planck volume distribution that we have solved depends on the choice of the time parameterization, which is not important in the quantum term or the classical drift term. These are all subdominant effects. The dominant effect is in the volume term, parameterized by this beta, where we see that it's determined by the ratio of F to M Planck, but also by this parameter psi. So in particular, if one takes a scale factor gauge where psi is 0, this is a gauge or a choice of time hypersurface that chooses equal scale factor across the hypersurface by construction. So this does not preferentially inflate one over the other, since one chooses equal scale factor. Then we just have a Fokker-Planck equation, and a lot of these dynamics, for example, would be very different. in terms of going up or down the potential. Now, it's important to note that we have not specified the inflaton sector. So a lot of the ambiguities in the measure problem when it comes to making predictions for what observers would observe at reheating is related to the reheating surface of the inflaton, which in eternal inflation is infinite. So one has to regulate this somehow. And this is where the choice of time parameterization becomes important in how one chooses to regularize this infinity. In the context of our phi distribution, this is not, this is an independent distribution that would reach the reheating surface and is not related in a straightforward way to the choice of time parameterization in the inflaton sector. So this is not to say that there isn't a measure problem for phi, but there definitely is not necessarily a measure problem for phi if there is one for the inflaton. This essentially motivates further study to understand this better in the context of self-organized localization in eternal inflation. Okay, so finally, we'll end there, and I'm happy to discuss more. Thank you.
Okay, thank you for this very nice and informative talk. It was quite clear. So, and we actually have ample time for questions and comments from the audience. Please feel free to ask directly.
Hi, maybe I can ask a question. If I understood correctly, there's no clear prediction what one should discover in your scenario. It's something more conceptual. Only that probably if one would discover something that gives another solution to the problem, then this would speak against your new idea. Do I see this correctly, or is there something to say, yeah, you should see something like this?
Yeah, so the let's say smoking gun, or not the smoking gun because it could be due to many other things, but the unavoidable prediction is that there is a rolling scalar field now. So this would be a non-zero W parameter. Now, whether it's measurable or not is something else, but that would be something that we would observe. In terms of other concrete predictions, for the Higgs naturalness solution, this would definitely require new physics at the TeV scale to lower the instability scale. So vector-like fermions at the TeV scale, I think, is a rather solid prediction in that context.
Can you give an upper limit on those, or where would you expect?
It's a similar thing that as composite Higgs, where the higher the instability scale, the more of a little hierarchy problem you have and the more tuning you have. So there it depends on if we discover vector-like fermions and if we can probe higher energy scales where we find that nothing is restoring the potential stability, then it would be, in my opinion, quite suggestive. But other than that, you're right that it's a more general framework that we could only indirectly infer from other potential BSM signatures that we may observe, such as phase transitions that we could observe through gravitational waves may give us some handle on a scale of phase transitions that would tell us more about our vacuum. But it depends in particular on what scenario one looks at. So
you have a lot of freedom there still, no, in this respect.
Yeah, this is to be thought of as more of a general framework. And again, there's many different possible realizations. And we haven't thought about all the different possibilities for how different types of phase transitions could explain different features.
Okay, thanks a lot.
Okay, any more questions or comments?
I can ask a question, maybe.
Yes, please.
So I'm not sure I followed completely the discussion of the measure problem, but is it correct to say that unless you choose your time in a specific way, this is not going to work?
It depends what you mean by specific, in that we have a lot of freedom in choosing this psi, in that psi can be a range of values. And the only one where it definitely doesn't work is when psi equals 0. That psi equals, essentially, the question is more, what is the measure that one adopts? In some measures, psi equals 0. In other measures, psi equals 1. So it's more of a, well, in some sense, it's a philosophical question about what is the best measure.
Okay, so but this psi is just a way of parameterizing a certain class of times that you can choose, right? But I suppose you can also do other things, right? Use other functions there.
Yes, and it's
not just this exponent, right?
Yes, exactly. It's not even about the time parameterization, and that the procedure for solving the measurement problem is different in different solutions. So it also depends on how one chooses to quantify the reheating surface and the observables at the reheating surface. The simplest thing that people did early on is just to choose a time parameterization and then take that time to infinity and then look at the stationary distribution as we're doing. So this time cutoff measure is, let's say, the simplest naive measure. But since then, there have been many proposed, and it's not just about choosing a time parameterization, it's a whole procedure for how to make sense of quantities. So this is why I say it really depends on looking at a specific approach to solving the measure problem and how that translates then to the distribution that we calculated for solve.
Okay, thank you.
Okay, any more questions? Okay, if not, then we can thank the speaker again. Thank you for this very nice seminar again. So I can stop the recording.